This is Chapter 10, Problem 41. Here we have what appears to be a really nasty arrangement of masses and rods, thin rods, and we need to calculate the rotational inertia and the kinetic energy as it moves about with a given angular velocity omega. So this gives us an opportunity to kind of experiment a little bit with the parallel axis theorem, and also to remember that when we have an arrangement made of several different objects, all we have to do is calculate the rotational inertia for each one individually and then add them all together. I'm going to handle the individual small masses first, since those are point masses, and we can solve for the rotational inertia of each one of these masses. I'm going to solve for I1 and I2, and all that is just md squared, the mass of the object multiplied by its distance from the rotational axis. So for the first mass, that's going to be 0.85 multiplied by 0.056 squared. And we get an I1 equal to about 0.0027. There's a little bit of a rounding error on this problem. Don't stress too much about it as long as you get close to the right answer. For the second mass, now we're a distance of 2d away from the rotational axis, so this is going to be 0.85 multiplied by 2 times 0.056, make sure to put that into meters, squared. And we get an I2 value equal to 0.011. So that takes care of the first two objects. The first thin rod should look very familiar because I think we've solved this in class 4 or 5 times. We know that the rotational inertia through one end of a thin rod is equal to 1/3 ml squared. If you don't remember that, then start off with 1/12 ml squared and then add the parallel axis theorem. So for the first thin rod, we have 1/3 of the mass, 1.2, times the length, 0.056 squared. And so I3 is going to be equal to 0.0013. I4 is the last one, and it is the most complicated. We're going to use a combination of the parallel axis theorem. Here I'm going to start off with our table on page 255, so 1/12 of ml squared. I could have used 1/3 ml squared, but I'm just using 1/12 just because. And now I'm going to add to that plus mh squared. And we have to be careful about the calculation of our h. H is now 3/2 of d, because the rotational axis is 3/2 d away from the center of mass of the second rod. So now we're going to get 1/12, the mass 1.2, multiplied by 0.056, that's the length of the rod, squared, plus 1.2 multiplied by 3/2 of d. Look back at the picture. The center of mass is going to be halfway in between that thin rod, so it's a half a d, and then it's another d away from the rotational axis. 3/2 of d is 0.084 squared. And so for I4, we're going to get 0.00034 for the first part, plus 0.0085 for the second part. Adding everything together, we get an I total, again a little bit of rounding here. Adding I 1, 2, 3, and 4, we get 0.024 kilogram meters squared. Final part I really don't have to calculate because calculating the rotational inertia was the hard part, but now the kinetic energy of rotation, just to review, is 1/2 I omega squared. They gave you omega, so just square it, multiply it by I, and divide by 2, and you have the kinetic energy.